Hello everyone and welcome to Tech Talk session 22. Yes, 22. So today we are talking about transient outrush reactors. We had a Tech Talk a while back that we talked about transient inrush reactors as used in metal closed capacitor banks. Today is transient outrush reactors. So a very interesting topic, and you know, if we were to gauge the number of metal closed systems that utilize transient outrush reactors, it would be roughly maybe 10%, or not even that, maybe 5%. But outrush reactors are typically specified in the larger metal closed capacitor banks that we utilize in the renewables industry. So whether it's wind or solar, we get up into this 20, 30, 40 megavar range, maybe 50 to 60 megavars, and outrush reactors are often specified. So we're going to be talking about this thing called outrush reactors, why you need them, what they are, what they look like. And at the end of the presentation, we are going to go out to the factory floor like we did last week. We will walk on top of a piece of equipment and show you a transient outrush reactor installed in our gear, or on top of our gear in this case. So we're going to get on with the presentation, and I want to remind you that, again, there's PDH contact hours. Don't forget to send us an email. As you know, we respond right away. We get those contact hours back to you. You can apply those towards your continuing education credits. We normally have Rodrigo Dunner from our South America, Santiago, Chile, on our calls to help translate Spanish questions. He is not with us today. He's had some technological issues, but you can send a message in Spanish if you like, and we will certainly respond in English, and then Rodrigo will translate it in writing in the chat box should you have questions. And also don't forget what NEPSI does. NEPSI is a manufacturer of metal closed capacitor banks, harmonic filter banks, the Activar product which starts large motors. And what we are showing you here is a piece of equipment that we had designed, built, and shipped to a wind farm. And in particular, I showed you a little yellow circle around what we are talking about today, which is outrush reactors. So this was a single stage 4.1 M bar shunt inductive bank with a switch inside it to switch that inductor in and out to basically compensate or apply negative VARs, if you want to call it that, to the system, basically to reduce voltage. And it's also a two-stage cap bank. All switching protection control is built in, typical for metal closed systems. So that is what we do, and we're talking about these devices up on top in the circle here. And we will actually walk on top of a unit here on our factory floor to discuss that even more. So what is a transient outrush reactor, and why are they used? So first of all, a transient outrush reactor is a fixed inductor. It's just an inductor. And normally when we're talking about outrush reactors, we're talking about inductance values that are in the order of, say, 200 microhenries. So 0.2 millihenries, maybe 0.3 millihenries, 300 microhenries. Remember, outrush reactors typically have a slightly higher rating than those that might be used for transient inrush to a capacitor bank. So I'm going to put my mouse here and show you. These are transient inrush reactors. Transient inrush reactors. And these are installed, and we have a tech talk that we talk about these. They're there to reduce the back-to-back switching current that you might get in a metal closed system when the switching device closes. So if we had a situation where BH-1 and BH-2 was closed, and we were looking to close BH3, the charge current within these two systems over here, these two capacitor banks, we want to discharge into that third bank, and that BH-3, that breaker or that switching device, will be subjected to a very high DIDT, a very high peak current, and would have a high magnitude current and high frequency. And if you can think about it, as the contacts close, this very high DIDT would have a tendency to want to weld the contacts closed. So since a metal closed cap bank and even open air banks, the only impedance between one stage and the next is the impedance of the bus work or of the cabling. You're looking at maybe 0.5 microhenries per foot. There is almost essentially no impedance between the two. So in those situations, we would typically add about 40 or 50 or 60 microhenries between the stages, and that would have an effect of reducing the magnitude of current and also the frequency of current, so the DIDT would be reduced, and we would eliminate that issue of the contacts wanting to weld because of that very high rate of current. So that's the purpose of the transient inrush reactors. We had a tech talk that went through that. We will show one of those out back. Outrush reactors are different, and the outrush reactor is this one here on top. It's this one here, and that's an outrush reactor. So what we have in this situation is if we have a fault, and I want you to think about this, and this is kind of a complex concept. If we have a fault over here, where this X is, and the capacitor bank was operational, BH1, 2, and 3 were running, and this breaker, which is a feeder breaker to, say, a collector system, so you say you have a string of wind turbines, and those wind turbines are strung together with the cable coming out of BH4. If we had a fault somewhere on that system, the breaker would be closed, and the capacitor bank, because this was a faulted circuit, it would want to discharge into that fault. Now that's not in itself an issue. Typically there is no issue with that first initial fault condition. What happens at that point is the breaker is closed, and the breaker can handle that high current that you would get during that fault condition, during that discharge period. No issue there. The bigger issue now is that after the fault has occurred, this breaker BH4 opens. BH4 opens. The system is cleared. This capacitor bank would be put back into operation. It's put back in operation. It's energized. And they send some line guy out there to fix this cable or to figure out what's going on. Maybe he can't locate the fault. He blames it on lightning, which is a lot of times just a flashover event and it goes away. And he re-energizes BH4. He re-energizes BH4. Now in that situation, if there was a permanent fault, if that X represented a permanent fault, say he didn't locate that fault and it was permanent, the current that exists, or the charge that exists on these capacitor banks, will want to discharge into that faulted condition. And that breaker, more or less, now is making the current. It's actually almost like a back-to-back transient situation. It's actually making a transient, making current. In fact, the formulas to calculate this current is the same. They are the same. And so that's what the situation is. So just to repeat, to make sure it's clear, we have a situation where we have a permanent fault on BH4, and the capacitor bank here is running. Okay, so if the capacitor bank is running, we have a fault here at this location or somewhere along this line, and they energize this breaker into that fault. And the discharge current here will discharge through that breaker at that moment in time, and that is basically, you're dealing with the transient making current of the breaker at that time. And that is the issue. So very often BH4, BH5, BH7, they are just general purpose breakers. C0 rated breakers are not rated for restrike, and they can't handle that transient rush current, and that can result in breaker damage to the breaker. So when you do close BH4, the only impedance in the circuit that reduces the magnitude and the frequency, okay, of that current flow is the impedance of the cabling, the impedance of the buswork, and the impedance to the fault. That's it. And if it's a close-end fault, and we call it a close-end fault, say right outside of the substation, that would be a close-end fault. And think of this inductance of the cabling as 0.5 microhenries per foot. So whatever you have for distance, 0.5 microhenries per foot. It's a good rule of thumb. Sometimes maybe slightly less, but 0.5 microhenries per foot. It is that impedance that will limit that fault current. And so the objective of putting an outrush reactor is to add enough impedance to bring the DIDT, the peak current, the peak transient current that you would see at this location for a fault condition. That's really what we're looking for. So we have developed a calculator. We're going to go through that in a moment, on that you can use to do this analysis to determine whether or not you need an outrush reactor. Here, let me just check the rest of the notes here. Okay, we're good. Typically, they're air core reactors. Outrush reactors are air core reactors. So we have a situation sometimes when you have a main tie main situation, as we show here, and there's an open tie breaker. In this case, it's only faults on the same side of the tie breaker that will result in current flow. So think about this: if you have a main tie main system, you want to design the system for the condition where the tie breaker is closed, because the situation there is we have basically doubled, sometimes doubled the amount of capacitance or the amount of discharge current into that fault condition at that location. So when doing the sizing calculations to determine the reactance required to do the analysis, make sure that if it's a main tie main, that you consider the tie closed in your calculations, and that's really the true value of inductance that you will want. The other thing you want to make sure you do is you want to make sure that you include any inductance in the capacitor bank itself. So if you have transient inrush reactors here, okay, you can add that inductance. Basically, it'd be 1/3 of the inductance. Here we have 3 in parallel, so it'd be about 1/30 inductance, and that would help to increase the current flow. But this inductance here, it will be added, 1/3 of that impedance will be added to this inductor here. And our spreadsheet tool essentially does this calculation for you, but the effect of having transient inrush reactors is to reduce the amount of inductance required by your outrush reactor. I hope that didn't confuse you, because it's a lot of information. So the other thing you have to think about is the type of fault. The type of fault in the capacitor bank connection. And the first thing to realize is that metal enclosed capacitor banks, actually all medium voltage cap banks, are typically left ungrounded. They're left ungrounded, which means that if I have a line to ground fault, somewhere out in the feeder, and the cap bank is ungrounded, and I fault, say, a single phase cable, okay, I will not get current flow. The loop is not completed because the neutral of the cap bank is ungrounded. You can't draw a loop around that whole circuit, so therefore there will be no current flow for a ungrounded cap bank into a grounded fault condition somewhere outside the substation. So this is something to always think about when you're thinking about adding outrush reactors to your cap bank. Think about the type of fault you have, and also think about the connection of your cap bank. So I would say, by and large, nearly all banks are left ungrounded, which means that for all line to ground fault conditions that exist outside the substations, the capacitor banks will not contribute fault current. If you're thinking about a phase-to-phase fault, the condition there would be like radical 3/2. It would be the typical value. It's not 100% of the three-phase value. It's a percent of it. So that outrush current will be, again, less what that breaker has to withstand. If you have a substation that's using cables that leave the substation, so you have your switchgear line up inside the substation, you have your cap bank there. A lot of times when people are doing the transient outrush calculations, they're applying a fault at the breaker inside the substation. If the cables are coming into the substation and connecting to those feeder cables, the possibility of a three-phase fault on that cable is very, very low. Think about a shovel going into a cable, into a ditch like this. It's not going to pass through all 3 cables instantaneously. It's going to pass through 1 cable at a time, right? And therefore, we're going to go line to ground first. That would trip the circuit breaker upstream. It would clear that fault before the shovel got through that second cable. So I think it's an engineering call when you have cables coming into your substation. The amount of inductance that you use in your calculation to the first location of the fault is what matters. Okay, so maybe I should show this on the iPad real quick, because I didn't have time to really show it. So if you have a bus bar and you have a cable here, and then we go out of the substation, and at some point you might go up overhead, right? You might go up overhead and have some kind of overhead line. The cap bank being here. So you have some large cap bank here, say 40 MVAR. And if there's a fault, so the question becomes, where can we have a fault? Okay, where is the logical location to have a fault? And certainly you could have inside the switchgear there. You could have inside the switchgear there. And that means that the inductance would be the inductance inside the capacitor bank itself, plus the outrush reactor, plus the impedance of the cable, and then you have the distance to the actual breaker itself, that inductance. So we would typically be about 0.5 microhenries per foot would be the value of inductance that you might want to consider. And but if you have a fault inside the breaker has failed. So in my opinion, that's not a valid location for a fault. And you would want to then maybe move along this cable and say, well, where can I have a three-phase fault? And in my opinion, the first location is here. First location is there. And that might be a pool, maybe a, what do you call it, a place where you have a place where you pull the cable through, or a riser going up a pole, but somewhere out there. Is it realistic at that point you can have a three-phase fault or a phase-to-phase fault? And so it's that inductance along this full length here that you want to consider. So inductance here, L1 plus L2 plus L3, and then plus L4. And it is this inductance here, that total inductance might be enough that says you don't need this. And that's really the thing to evaluate. What is the possibility of a three-phase or a phase-to-phase fault along this length? And if it's cable, it's very low. The other thing to think about is most distribution faults are single phase to begin with. They are single phase to begin with. So you have another engineering decision to make. Okay, do I add this cost, add dimension to my equipment for that? And this is really all part of judgment when you're designing your system. But that is something to think about, is the type of fault in your capacitor bank connection. And if you do that, you will see that you may not need those outrush reactors. So we'll continue on with the presentation here, and we have a calculator on our website. If you go to NEPSI.com, navigate to resources, and then go to spreadsheet tools, you will find a calculator. And within that calculator, you will be able to insert your values of inductance, your capacitor bank size, the system voltage, and it will basically do the peak outrush current, the outrush frequency, and the I times F product. So this spreadsheet tool, I'm not sure, I probably won't review it today, but I might take an opportunity to bring it in after our factory talk if we have time. I will walk through this spreadsheet tool. It's going to calculate, again, peak outrush current, output outrush frequency, and the I times F. And you take those values and you compare it to the feeder breakers within the substation. And you want to make sure that you don't exceed the rating of the breaker. So in the end, this is part of your design process is, okay, what type of feeder breakers am I using? What is the possible outrush current and outrush frequency? What is the IF factor? And you compare the calculated value against those ratings. If you exceed the ratings, then you need to add some inductance. And the question is, well, how much inductance? And use the spreadsheet tool and you just iterate. Okay, let me try 50 microhenries. Let me try 100 microhenries. Let me try 200. And then once you get to a certain value that works, then you know your inductance value to use. It's also worth noting that the spreadsheet tool has the various standards in there. It describes how the calculation is done, number one, but then number two is how to actually make this comparison. And we actually have some tests, and we show that test here in the bottom of the spreadsheet tool. So perhaps after the factory talk, we'll just walk through the spreadsheet tool. But it's a great tool. We have one for transient inrush, and we have one for transient outrush. And so you can actually view both calculation procedures. The calculation procedure is essentially the same. It's essentially the same, but the setup of the spreadsheet is slightly different. When you look at the typical or possible arrangements, we oftentimes will put our outrush reactors on the roof of the enclosure. And the reason being is because they're really large. They're large reactors, large air core reactors. We got a question.
Yeah, Paul, we have a question from Christian. Are there cases in which increasing the inrush reactor inductance is more cost effective than installing additional outrush reactors?
That's a good question. So if you're using, I would say, first of all, if you're in a renewables environment and you have capacitor banks, and you have to, unless you're using some point on wave switching, like the VD4CS or some other type device, or you're using a Southern States cap switcher, which has a pre-insertion resistor technology, you're going to be required to put some type of transient inrush reactors in the bank. There is a thought, and what Christian has just noted here is that, well, perhaps I can increase the inductance of the transient inrush reactors to a value to also solve the outrush issue for the feeder breakers within the substation. And the answer is we have sometimes have seen that to be effective. And you have to think about, if you have a three-stage bank, I got 1/3 the current in each of the stages, right, of the total, or I can put one large reactor on the output. And so I think it's a good question. I think you have to do the economics, and we sometimes will. If we're being asked to do outrush reactors, our first thought is, well, if we need inrush reactors, let's see what it's going to take to get to where we need to get to limit that outrush current to the correct value. In a spreadsheet tool that we have, we'll do that. You can put the inrush value in there, the inrush transient reactor values, the inductance. Typically is 50 microhenries for a 38 kV bank. That's the minimum. So you think about that for a three-stage bank, the equivalent inductance is 1/3 of 50. So we're only at that point, or whatever the math is there. And that's really a small value in comparison to what we typically would see for an outrush reactor, which might be 200 microhenries in total. So I think very often we try to do the calculation, and the end result is we still have to put outrush reactors in. So good question, though. And so we'll go back to this this slide. And again, I appreciate questions. I think it's good for everybody to hear these questions. When we put the outrush reactor on top of our enclosure, what we are expecting at that point is that the customer is going to come in from overhead. And in the renewables environment, this is very common. They have their collector system, they got breakers within the substation itself, the bus work, and they'll park the metal closed system somewhere close by to that bus work, and they can jump down with a set of jumpers to our equipment. And that's shown by these red lines here. So they will come right into those outrush reactors. Sometimes it makes sense to orientate the equipment in a different direction. And when we do that, we might change the buswork structure on top in the layout of these bushings here, such that we can have cables come in through the back or through the sides. So it really depends on the substation design, but just know that the outrush reactors, typically the space required between them is greater than what would typically be required for the incomer of the capacitor bank. But with bus work up on top, we are able to orientate the incoming power cables in any of the three directions, either the front, the back, or the side. And this is something that is really an option. We're going to actually look at a piece of equipment out back that will show how we're doing this. So just kind of continue on. This is a typical outrush reactor. We just took some clips of a typical outrush reactor. It is much bigger than transient inrush reactors. And in this particular case, this outrush reactor is 224 millihenries. Well, yeah, 0.224 millihenries, 224 microhenries, 700 amp rating associated with it. So it's pretty large. And it's important to note that when you're installing these reactors, that you do pay attention to the magnetic field clearance requirements, and that's the MC1 and the MC2 requirements. Basically, the reactors will have an envelope around them for which you cannot have conducting parts, either large or small. The MC1 being large, MC2 being small. parts. If we have steel parts in that vicinity, the magnetic field flowing through the metal will create an eddy current. That eddy current causes heating. So we are dealing with a much bigger space because of the size of the reactor. So in this case, 700 amps, 224 microhenries. That's a lot different than a 40 or 50 microhenry reactor used on a single stage basis. We do not typically have to deal with the heating effect as much when we're dealing with transient inrush reactors as we do with outrush reactors. And then this is the other thing to take note is this reactor here, which is the one that you will be looking out in the factory floor, is 304 pounds. So it's a pretty heavy reactor. So when we put it on a roof, we have to reinforce the roof, not only for the snow load, but also for the weight of the reactor, and then also the torque that might be pushed onto the reactor from the cables or the buswork that is connected to the reactors. So these are all things that we have to consider. So just a quick, as dimensional, we're dealing here with 51 inches tall. So they're pretty tall reactors. We typically like to do an increased impulse level up on top because of snow and because of possibility of bird contact and things like that. We're typically trying to bump up at least one BIL level on top as a standard to improve reliability. Anyway, so let's pass on to, there's some reading that you might want to think about if you're dealing with this issue or this subject matter. The C3706 2009 standard addresses the breaker ratings. The application guide for power capacitors, and in this PES-TR16 technical report. These are all great resources. Our spreadsheet tool has certain snippets of this information, and the relevant portions of the standard are highlighted to dictate where you should be watching out. So it's a great tool. And we got another question.
Richard is asking, would you ever use an iron core reactor for an outrush reactor?
That's a good question, and we do on occasion we do outrush reactors, but by and large outrush reactors are air core, not iron core. And oftentimes there's fault currents that are fault current. The reactors are requested to be fault current rated, and as such the epoxy impregnated type reactor that you see from companies like Trench are well suited for that application. But we do have one customer that does use iron core reactors. So again, it's something I think it's a good question, and iron core reactors are possible. You have to be careful with the design. You got to make sure you specify them correctly. Because remember, a iron core reactor that you use as a filter is different than the reactor that you would use for outrush. So you have to make sure that the outrush reactor, that iron, does not saturate for the outrush current. You have to be able to conduct that current. You want to make sure that the inductance is linear through the full wave shape of that outrush current. Otherwise, you lost your inductance and you lost the effect of the iron that makes up that iron core reactor. So good question. You have to be very careful. Air core reactors are easier because there is no saturation concern. So we typically move in the direction of air core reactors and not iron core reactors. All right, so I'm going to be going out to the factory floor. Just like last week, I'll be back with you in maybe a minute, and we'll see you in just a few minutes. All right, in the shop. So before we get going on the this capacitor bank, let's talk about transient inrush reactors. We had a tech talk a while back about transient inrush reactors. Transient inrush reactors can help support the required inductance to reduce the amount of outrush current you get from your capacitor bank. But transient inrush reactors are typically smaller. I got a whole rack of transient inrush reactors here, and this particular transient inrush reactor is 47 microhenries and 300 amps. So 47 microhenries, 300 amps. You can see kind of the construction. We put this into the bus bar structure of the capacitor bank, and normally it's put on each stage, and it limits the back-to-back transient current associated with back-to-back switching in the capacitor bank. So 47 microhenries. When we're talking about outrush reactors, let me put this down, it's heavy. When we're talking about outrush reactors, typically we're talking about inductance values in the order of, say, 200 to 300 microhenries. So transient inrush reactors will reduce the back-to-back switching transients within the bank for the switching device within the bank. The outrush reactors are designed for, again, for the feeder breaker outside of the capacitor bank, those that feed the collector system within a wind farm. So think about that. It's the total impedance or total inductance from the capacitor bank to the location of the fault. So these transient inrush reactors will help to reduce the rating of the outrush reactors, which we're going to talk about in a moment. So let's just talk about this piece of equipment for a moment. This is a 40.5 MVAR capacitor bank, 34.5 kV rated, and it's got a BIL rating of 185 kV BIL. So it's a three-stage bank, and we're going to kind of walk along here. You can see this is stage 2. We got a window and a ground switch, and then we got a switching device. We're going to talk about this switching device today. It's a VD4CS, and then we have another, in this case, 13.45 megavars, another ground switch, and then a switching device. And this is the construction. It's a fully assembled piece of equipment. We have to split this bank in two because it's greater than 40 feet, so we split it in two. And that's what you're looking at here. You're looking at a piece of steel that will come here to cover the gap between the two enclosures. So let's just talk about the switching device, because this is the new ABB VD4CS. It's a transient-free switching device, and it's installed within this system. So what you're looking at is the ABB VD4CS. It's a transient-free device. It's point-on wave switching. It has a rating of 38 kV, 185 kV BIL, 31.5 kA short circuit current, and a 1200 amp rating to it. So it can switch 1200 amps of capacitive current. It's a significant amount of capacitive current. It uses servo motors within this device here to accelerate and decelerate the contacts so that you get the precise point-on wave closing. Okay, this is a relatively new device. It's an alternate to the Southern States cap switcher, which uses pre-insertion resistor technology. So this is using point-on wave, looking to basically close on zero voltage. We have recorded several videos on this technology, so we won't get into it too much. It has a 10,000 operation count to it for a warranty and a 5-year warranty. So 5 years or 10,000 operations. It's stock at NEPSI, and that's key, stock at NEPSI. So if you have an issue with delivery time, you can come to us, and we're going to be able to ship you a cap bank within a very short period of time, because we're stocking these at NEPSI. It's something we can't do with the Southern States cap switcher, unfortunately, because of the resistor size. The resistor size, which is the pre-insertion resistor, really is sized based upon the MVAR rating of the capacitor. So if you just poke your head in here maybe a little bit, and you can see this is the voltage sensor. So we're connected to phase A line side, and we're sensing the phase A voltage, and we're closing on zero voltage, okay, with this device. And the electronics and the knowledge of when to close is inside this switching device. You can see that we have some line side lightning arresters. That's a specification requirement for this project. And it's in a isolated cubicle. It's in its own compartment, and we've insulated the compartment. And we do that because this has a temperature rating, a minus 20 degree Celsius temperature rating. So we're looking to maintain the environment inside here. So we insulate this complete compartment. We use through-wall bushings between the compartments, and we heat this compartment to a value of temperature that's within the rating of this device, plus some for margin. And that's really the purpose of that. It's easy to change out. You got a quick connect here that you can release to pull the device out. And incidentally, we designed these compartments so they will house both a Southern States cap switcher or a VD4 CS. So that's really the essence of this I wanted to talk about for a moment, because it's still a relatively new device. Remember, it's got a fault rating to a short circuit rating, a short circuit interrupt rating, which you can use to eliminate the feeder breaker to the capacitor bank. So it's a cost-saving device. So I'm going to climb up the stairs over here, and as I'm doing that, we're going to walk on top, and we're going to talk about the transient outrush reactors up on top. So let me go up these stairs, and I'll see you guys up on top. All right, okay, I'm coming. All right, so you're looking at the transient outrush reactors here. And just to make sure I don't fall, I'm going to step between these main bus bars. So these are a roof-mounted transient outrush reactors. You can see when we compare this to the transient inrush reactors that we were using for back-to-back switching, these reactors are much more substantial. So these are right here are rated 227 microhenries. So oftentimes you might say 0.227 millihenries, but they're 700 amps, 0.227 millihenries, and they're on the input to this entire 40.5 inbar system. So they're the input. So there's a lot of current to it. So let's just talk about the customer connection point first. In this case, the customer is connecting to the terminals on the outside here. They actually have their bus work over here associated with their substation network, and they're going to cable down to these 3 reactors. So you got a phase A, B, and C set of reactors. Those reactors are bussed into these bushings here. All right, so we have bushings here. These bushings is what provides the power flow through the roof of this enclosure and then finally into our metal enclosed system. So these are a 250 kV BIL bushing, and we got the main bus work here. So air core reactors here, we can orientate the reactors so that you have entry from this side, entry from the front, or entry from the back. And what we do is we situate and move the bus work around here as well as the bushings here to allow for entry into the enclosure through either through the sides, the back, or the front. And that's really the essence of this air core reactor arrangement on the roof, is to do that. When we ship this equipment, we can't ship with all this structure on top because we're beyond that 10.5 feet that a truck might require for clearing access underneath bridges and stuff like that. So for highway permitting purposes. So all this is removed before we ship. We ship this in a separate container, and it goes to the site, and it gets mounted at site. This is the typical outrush reactor arrangement when we do a roof-mounted arrangement. Remember, we can also put these reactors inside the enclosure, and when we do that, it means that the compartment underneath has to contain these devices. And because they're air core reactors, they have a lot of magnetic field, and that magnetic field requires that we have clearance to the metal parts. So we have to make sure we don't get eddy current heating in the metal parts. So those reactors, when they get placed into the enclosure here, we go up about 10 foot in dimension. So we're going to increase our enclosure dimension by at least 10 feet, and we sometimes have to increase the depth. But there is the ability to put these inside the equipment. So we're going to head back towards the shop. So I will see you in a minute. Let me head back to the shop, and we'll finish up the tech talk in the office. I'm sorry, in the office. All right. I'm doing tech talk. Okay. All right. All right. So I'm back with you, and new question. I like questions. Okay.
Yeah, Paul, you got a question just as you were coming back. So Syed says, which type of air core reactor is a better choice? So in your opinion, copper wound or an aluminum wound?
You know, I have no opinion on that. We typically leave that to the supplier of the reactors. We're not a manufacturer of reactors, so our preference is to leave it to the experts, those who wind reactors. I think for the most part, those that you're seeing out there are in fact aluminum, but I really do not know the difference, which one will be better. And personally, from our standpoint, we would leave it to the experts who are building those reactors to make that decision. So we're going to go over to the spreadsheet. We're about 45 minutes in, so we'll go to the spreadsheet. We have a little bit of time, and again, this is on our website, and you navigate by going to resources. So www.nepsi.com. Then you go to the far right, you'll see a resource tab. Underneath that resource tab, you see YouTube videos and calculators, and there's a part where it says spreadsheet tools. And if you've been there, we have filter design tool, we have outrush calculator as you see here, and then we also have an inrush calculator and some other calculators, but these are spreadsheet tools. And if you look at our spreadsheet tool, one of the things that's interesting is we have different tabs. We can go to different tabs, and on each of those tabs, we have various pieces of information. The yellow fields are always is the fields that you enter. We always have a background information. We explain exactly what is going on in these spreadsheet tools, the concept of what we're trying to do, the calculation basis, the formulas, and then what the values of input. So this is a really easy spreadsheet tool. You put in your values of microhenries for your outrush reactor, for the incoming cables, assume about in this case we're saying 0.2 microhenries per foot. So I mentioned 0.5, the value is 0.2. My memory is going as I age. You also have to put in your capacitor bank voltage. It does change the outrush value. Do the calculation at the peak voltage, not at the normal system voltage, because at peak voltage you will have a higher output. So do it at peak voltage rather than nominal voltage. System frequency, and then the kVAR of the bank, and then finally the actual transient inrush reactors. So in these spots here we have the transient inrush reactors, and over here we have the inductance between the fault and the capacitor bank. So basically that's the cable and the bus work, but it doesn't include the actual inductor itself. That is here. And if you can think about what we're doing here, we're just adding the inductance up. Inductance from the fault point to the cap bank, in other words, the bus work and the cabling. Then we got the inductance associated with the outrush reactor, and then we have the inductance associated with each of the three transient inrush reactors. And they may or may not be present. Remember, if you're using transient mitigation technology such as a southern phase cap switcher or the ABB VD4CS, you don't need transient inrush reactors, so they would not be present. And so that's something to think about. And then from there, we will calculate the various values, the surge impedance of the system, the outrush current, the outrush frequency, and its IF, which is the outrush peak current times so it's the IF product, so it's the peak current times the frequency. Basically, it's giving you the IDT, and it's got a kilohertz value, and we can use that information and compare it up against the breaker ratings. And you know, depending upon what type of breaker you're dealing with, if it's a C0 breaker, meaning it's not really designed for capacitor switching, there is a possibility of restrike. You have a set of parameters that you're evaluating for that breaker, and then you have a C1 and a C2 rated breakers, which are those that have a lower probability of restrike. Remember, C1 is low probability of restrike, C2 is very low probability of restrike. And you can go to the standards, and that's actually on tab 2 of this spreadsheet tool, C3706, and in there you can find where they talk about the C0 rating, and we make some notes over here about these various footnotes within the standards and what the C1 and the C0 rating does for you, as well as the tables that are associated with those standards. So we're just peeling apart the standard a little bit and telling you, hey, these are the parts that matter. So you don't have to go review the whole standard. There's also another standard that speaks to it, and that's C37, standard 1036, 2010 standard. And it also talks about outrush current. And what's interesting about this note here is that there are situations where for very small capacitor banks, the frequency can get very high. So if you start looking at the I times F factor, if you have a very small bank, like say you have a surge capacitor 0.5 microfarads, you can get a very high frequency, and it takes that IF factor sometimes beyond the breaker rating. And just common sense says, hey, if I got only a surge capacitor, do I really need to put a outrush reactor associated with it? And common sense says no. So that's what the standard speaks to. But if you strictly follow C3706, it would say, yeah, you need to put outrush reactors in there. So you have to kind of put on your design hat and decide what's necessary for the project. But I can tell you, surge caps, you would not typically see an outrush reactor. For a very large cap bank, you would. Remember to always evaluate the type of fault that you have, and the type of fault that you have, where the fault might occur. The fault does not always occur within a switchgear. Remember, a fault inside a switchgear is a switchgear failure. Trying to save the breaker with outrush reactors in a cap bank would not make sense. So put your first fault point someplace outside the switchgear. You know, is it within the substation itself? If you're coming in with cables, it belongs further out. And then think about whether or not what your probability of a three-phase or a phase-to-phase fault is in a capacitor bank connection. Can the capacitor bank contribute fault current to the system or not, or through that breaker? So these are things to evaluate. And then finally, if you have outrush reactors, perhaps you can specify C1 or C2 breakers for the entire substation. What is the cost differential to put all C2 rated breakers within the substation? Okay, and if you put all C2 rated breakers within the substation, many times the outrush reactor is not required. So this is part about really understanding what the outrush current issue is, and is there other ways around having to put outrush reactors in a system. And one of those ways around it is C2 or C1 rated breakers in your substation. You'll get away with a higher outrush current. So that about finishes up for today. We'll go back to the presentation for a moment. And I kind of already stated the conclusion. The PDH contact hours, just send us an email. The code is 311. And next week, we have, I think, by far the best presentation that we will have had so far. We're going to go out to the shop and we're going to do an in-post test on the system. And we will show you the in-post test equipment and how it works. We will talk about the importance of the in-post test, how our in-post test reports look, and then we will do the in-post test actually live on a piece of equipment. And what will be the best part is we will put a defect into the bank and show you how the in-post test set will pick up on a manufacturing error. And one of those errors might be putting a piece of bus bar up, connecting it, and pushing a bolt through too far. Your manufacturer, the guy assembling the equipment, might use a 3-inch bolt when he should have used a 2-inch bolt. And he has a phase to ground violation that can result in flashover. So we're going to actually do this in post. Jessica, I think Peter will be with us next week to do that in the factory floor. So we will start here in the office again, and then we'll go to the factory floor and review this in post test for next week. So we'll see you. Thank you for attending.